Most industrial systems don't fail because of bad technology, they fail because they don't scale. At small capacity, everything looks perfect. Machines run smoothly, output is stable, operators are confident, it feels like the system is working. But then demand increases. Suddenly, delays start showing up. One machine begins to struggle. Materials start piling up. Operators start improvising. What used to be smooth turns into chaos. Same system, same equipment, completely different outcome. This is the reality of industrial engineering. A system that works at 50 units per hour can completely break at 80. Not because it's broken, but because it was never designed to grow. And that's the real problem. Scalability is not something you add later. It's something you design from the very beginning. In this video, I'm going to show you how real industrial systems are built from scratch, not just to work, but to scale. Before you build anything, you need to answer one simple question. What exactly are you building, and why? Not in vague terms. Not a production system or a processing line. You need clarity. Are you building a system to move material, to transform it, or to store it? Because each purpose leads to a completely different design. Then ask, who actually needs this system? Is it driven by real demand from operations, customers, or market pull? Or is it just an internal assumption? Because building without real demand is how systems become expensive, oversized, and underutilized. Now we get into the numbers, the part most people underestimate. What is your target throughput? How much output per hour, per day, per shift? This number defines everything, not guesses, not around this range. It has to be specific. Next, what level of quality is required? Are you moving bulk material where variation is acceptable, or precision products where consistency is critical? Because higher quality always means tighter control, slower processes, or more advanced systems. And then, how will this system operate? Is it running continuously, 24/7? Or in batches? Will it face peak loads, seasonal demand, or unpredictable spikes? Because a system designed for steady flow behaves very differently from one designed for fluctuation. Here's the reality most people ignore. If you skip this step, everything that follows is built on assumptions. And assumptions are dangerous. That's how you end up over-designing, spending too much on capacity you never use. Or worse, under-designing, creating bottlenecks that choke your entire operation. A scalable system doesn't start with machines. It starts with defining the problem and the demand, clearly, precisely, and based on reality. Once the problem is clear, the next step is mapping the process. You break the entire system into simple, logical steps. Not complex, not detailed yet, just clear. Everything starts with three things: input, processing, and output. Where does the material come from? What happens to it? And where does it go next? You're turning something abstract into a visible flow. Raw material comes in. It moves to machine A, then to machine B. Then to storage, then to delivery, step by step, no gaps, no assumptions, because every missing step becomes a future problem. This is where you stop thinking in terms of machines and start thinking in terms of flow. And to make that flow visible, you use simple tools. A block flow diagram gives you the big picture. Just boxes and arrows, no complexity, just direction. Then you refine it with a process flow diagram. Now you start adding detail. Connections, sequence, logic, still simple, but structured, because the goal here is not perfection. The goal is clarity. Here's the reality. If the flow is unclear at this stage, scaling later becomes chaos. You'll have materials going in the wrong direction, bottlenecks appearing where you didn't expect, systems that fight against themselves. And once the system is built, fixing flow is expensive. So this step matters more than it looks. A scalable system is not built on equipment. It's built on a clear, logical, and well-defined flow. Now we get into the part that defines whether your system will actually work at scale, capacity, and bottlenecks. Every step in your process has a limit. Machine by machine, conveyor by conveyor, storage by storage. Your job is to calculate the capacity of each one. Not roughly, not based on assumptions, real numbers. How much can it handle per hour? Per minute? Under real operating conditions? Because here's the truth. Your system is not as strong as its best machine. It's as weak as its slowest one. This is the core concept most people miss. Your system capacity is equal to your bottleneck capacity. Nothing more. You can have a conveyor running at 100 tons per hour. Fast, efficient, no problem. But if your crusher can only handle 80, then your entire system is 80. Not 100, not almost there, it's 80. The extra 20 doesn't disappear. It becomes buildup, delays, pressure inside the system. And that's where problems begin. Material starts queuing. Machines start waiting. Operators start reacting instead of controlling. And suddenly, your high-capacity system becomes unstable. This is the reality. Most industrial systems fail right here. Not because the machines are bad, but because the system is unbalanced. One part is too fast. Another is too slow. And the whole system starts fighting itself. A scalable system is not about pushing everything to the maximum. It's about alignment. Every step matched. Every capacity understood. Every bottleneck identified early. Because once the system is built, fixing imbalance is expensive. But designing around it from the beginning, that's what makes a system truly scalable. Now you choose the equipment, and this is where most decisions go wrong. Because people don't choose machines based on systems. They choose based on price, brand, or what's available. That's how problems start. Equipment selection is not about picking the best machine. It's about picking the right machine for the system. First, capacity. Every machine must match your system flow. Not too big, not too small. Just aligned with your target throughput. Because when one machine is oversized, it doesn't make the system faster. It creates imbalance. And when it's undersized, it becomes your bottleneck. Second, reliability. Can this machine run consistently under real conditions? Dust, heat, continuous load, operator variability. Because in the real world, performance on paper means nothing if the machine can't survive daily operation. Third, maintenance availability. Can you maintain it easily? Are spare parts available? Do you have the skills on site to fix it? Because every machine will fail at some point. The question is not if, it's how fast you can recover. Now here's where most people make the biggest mistake. They overspec. They buy machines that are too big, too complex, too expensive, thinking it will future-proof the system. But instead, they lock themselves into high capital cost, difficult maintenance, and underutilized capacity. Or they go the opposite direction. They underspec. They choose smaller, cheaper machines just to reduce upfront cost. And those machines become constant problems, breaking down, slowing the system, creating hidden costs every single day. This leads to one harsh reality. The cheapest machine is often the most expensive in the long run. Because you don't pay for machines once. You pay for them every day they operate or fail to operate. A scalable system is not built with the most expensive equipment. And it's not built with the cheapest either. It's built with the right balance, capacity, reliability, and maintainability, aligned with the system, not just the budget. Now you have the right equipment. But where you place it, that's what determines whether your system flows or fights itself. Layout is not about fitting machines into a space. It's about designing movement. Material should move forward, smooth, direct, predictable. The moment material starts zigzagging, crossing paths, or doubling back, you're creating friction inside your system. Every extra meter of transport adds time, adds energy, adds cost. So you minimize distance, not just for efficiency, but for control. Then you eliminate cross-flow. Because when two flows intersect, you introduce conflict, delays, safety risks, operational confusion. A good layout is not just fast. It's clean. Now think beyond the flow. Can operators access the equipment easily? For operation, for inspection, for maintenance? If a technician needs to shut down half the system just to reach one component, that's not design. That's a problem waiting to happen. Then comes safety, clear zones, defined paths, separation between people and moving equipment. Because the fastest system means nothing if it's not safe to run. And one more thing most people ignore, space for expansion. If your system works today but has no room to grow, you've already limited your future. Because when demand increases, you won't scale smoothly. You'll rebuild. Here's the reality. Bad layout doesn't always fail immediately. It hides. It shows up later as unexplained delays, higher operating costs, and bottlenecks that shouldn't exist, but do. A scalable system doesn't just depend on what machines you use. It depends on how everything is arranged. Flow first, space second, everything else follows. You can have the perfect machines, the perfect layout, the perfect flow, but if your utilities can't support it, the entire system collapses. Because machines don't run on design. They run on power, air, water, and control. Start with power. Is your electrical system strong enough to handle full load? Not startup load, full continuous operation. Because when everything runs at the same time, that's when weaknesses show up. Voltage drops, trips, unexpected shutdowns, and suddenly, your high-performance system becomes unreliable. Then comes air and water. Compressed air for actuators, cooling water for temperature control, cleaning systems, dust suppression. These are not secondary systems. They are part of the operation. If pressure drops, machines slow down. If cooling fails, equipment overheats. If supply is inconsistent, your output becomes unstable. And then, control systems. Sensors, PLCs, feedback loops. This is what turns a group of machines into a system. Without proper control, everything becomes manual, slower, less accurate, more dependent on human reaction instead of system stability. And here's where most projects fail. Utilities are treated as an afterthought. Designed last, budgeted last, installed with just enough capacity. But just enough only works on paper. In reality, demand fluctuates. Loads spike, conditions change, and when utilities can't keep up, everything else suffers. Machines stop, flow breaks, output drops. A scalable system is not just about production capacity. It's about support capacity, power that doesn't drop, air that doesn't fluctuate, water that doesn't fail, control that doesn't guess. Because in the end, your system is only as reliable as the infrastructure behind it. Now comes the part most people think they can figure out later: scalability. But scalability is not an upgrade. It's a design decision. From day one, if your system only works at today's demand, you didn't build a scalable system. You built a temporary solution. So you design for growth before growth happens. You think in modules. Instead of one massive system, you break it into repeatable units. Each module does the same job. When demand increases, you don't redesign, you duplicate. That's how real systems scale. Then you think in parallel lines. Not one line running faster and harder, but multiple lines sharing the load. Because pushing one system to its limit creates stress. Replicating systems creates stability. This is the difference between vertical scaling and horizontal scaling. Vertical scaling means making one system bigger, faster, more complex. Horizontal scaling means adding more systems that already work. And in the real world, horizontal scaling wins. It's easier to control, easier to maintain, easier to expand, and most importantly, it's predictable. Then there's space. Not empty space by accident, but intentional space for expansion. Room for additional machines, extra conveyors, future connections. Because if your layout is already full, your growth is already blocked. And here's the reality most people learn too late. Retrofitting is expensive, not slightly expensive, 2 to 5 times more expensive. Because now you're not just building. You're modifying, stopping operations, rerouting systems, fixing what was never designed to grow. A scalable system doesn't chase demand. It's ready for it, built in modules, designed in parallel, planned with space. Because the easiest time to scale a system is before it's built. Now you connect everything with automation and control. Because without control, you don't have a system, you have a collection of machines. It starts simple: sensors. You need to see what's happening in real time. Flow rates, levels, speed, temperature, position. If you can't measure it, you can't control it. Then comes feedback. The system doesn't just run, it reacts. If flow increases, something adjusts. If pressure drops, something responds. If a machine slows down, the system compensates. This is what turns movement into stability. Then you layer in basic automation. Not to replace people, but to remove variability. Start, stop logic, interlocks, sequence control, simple rules that keep the system consistent even when conditions change. Because the goal is not complexity. The goal is stable output with minimal human error. Humans are good at solving problems, but they should not be the system. If operators are constantly adjusting, correcting, reacting, your system is unstable by design. Automation brings consistency. It reduces guesswork, reduces delay, reduces dependency on individual skill. But here's where many projects go wrong. They over-automate too early. They add complex systems before the process is even stable. Advanced control on top of a broken flow doesn't fix the problem, it hides it. And it burns budget. More sensors, more software, more integration, more cost, with little real improvement. A scalable system builds automation in layers. First, make the process work. Then, make it stable. Then, automate what matters. Because control is not about making things smarter. It's about making things reliable. Now it's time to test the system. This is where design meets reality. You don't go straight to full production. You start with a dry run. No material, just movement, motors, conveyors, sequences. You're checking one thing. Does everything work the way it's supposed to? Then you move to partial load. Introduce material, not at full capacity, controlled, gradual. Watch how the system behaves. Where does it slow down? Where does it hesitate? Where does it start to deviate from the plan? Then, and only then, you go to full load. This is the real test. Because full load exposes everything. Weak connections, hidden bottlenecks, control delays, mechanical limitations. And while the system is running, you measure. Output. Are you hitting your target? Downtime. Where are the interruptions happening? Efficiency. How much of your system is actually working versus waiting? This is not guesswork. This is data, because what you designed on paper is not what you get in reality. And that's normal. Here's the truth. The first run never matches the design perfectly. Never. There are always gaps, misalignments, unexpected interactions between components. The goal of commissioning is not to prove your design is right. It's to find where it's wrong and fix it. A scalable system is not born perfect. It's tested, adjusted, and refined under real conditions. Because only when it survives reality can it handle scale. Now you optimize and improve. The system is running, but this is where performance is shaped. You use real data, not assumptions. Look at output, downtime, and flow consistency. Where are the losses? Where is time being wasted? Every delay, every idle moment, every imbalance is a signal. You identify the bottlenecks, then you fix them, one by one. Not randomly, but based on impact. This is continuous improvement. Small changes, repeated consistently, create massive results over time. Because the goal is not perfection on day one. It's progress every day. Here's the reality. The system is never finished. Demand changes. Conditions shift. New constraints appear. A scalable system evolves. It adapts, improves, and gets stronger with time. Now you face the real decision. Cost versus scale. Every expansion is a trade-off between CapEx and OpEx. Spend more upfront, and you gain efficiency, stability, and lower operating cost over time. Spend less, and you stay flexible, but often pay more later in inefficiency and limitations. The question is not just how to scale, but when. Do you scale based on real demand, or on speculation? Because timing defines risk. Scale too early, and you lock capital into capacity you may not use. Cash flow tightens. Flexibility disappears. But scale too late, and the system becomes a constraint. You lose opportunities, delay growth, and fall behind demand. This is the balance. A scalable system is not just engineered, it's timed. Now let's talk about the mistakes that quietly destroy industrial systems. First, ignoring bottlenecks. You focus on speed, but one weak point limits everything. Second, no scalability plan. The system works today, but collapses when demand grows. Third, poor layout design. Material flow becomes inefficient, creating hidden delays and higher costs. Fourth, underestimating maintenance. Machines don't just run, they wear, fail, and need access. If maintenance is hard, Downtime becomes constant. And finally, overcomplicating automation. Adding complexity before stability only creates fragile systems. These mistakes don't always show up immediately, but over time, they compound and break the system from within. An industrial system is not a machine, it's a network of constraints. Every part is connected, and every limit shapes the outcome. You don't win by having the best equipment, you win by controlling the flow. Because flow defines performance, always. Then remember this. The bottleneck is the truth. It tells you the real capacity of your system, no matter what the design says. Ignore it, and everything else becomes noise. And finally, scalability is not luck. It's not something that just happens when demand grows. It's a choice you make from the beginning. Designed into every step, every decision, every connection. That's how real systems are built.